I think this section is actually pretty easy. If chapter 9 made sense, then I think chapter 10 will make sense. It's really just an extension of chapter 9. Um, so 10.1 is about comparing two proportions. 10.2 is about comparing two means. So um, if we're looking for proportions, so here's all the formulas and whatnot, but let's not worry about that right now. So basically, this section is all about, suppose we want to compare the proportions of individuals with a certain characteristic in population 2. Um, so for instance, like, we'll do an example that involves, we might want to see whether a heart disease or a drug that's supposed to reduce heart attacks, whether it works or not. So population 1 might be given that drug, and population 2 might be given a placebo. Um, or things like that. So um, what we're trying to do is compare the two populations. So another example here is suppose at one school, 70% of students did their homework last night, and at the second school, 50% of students did their homework last night. So suppose the counselor so first off, again, we're assuming we know this. All right, right? We can't really know this, but we're assuming that we know this information. So, so in the future, we won't know that. We'll just kind of have to guess at it, and we'll see how we can deal with that. All right, but so school one, 70%, school two, 50%. Um, and the counselor, school one takes an SRS of 100 students, and school two takes an SRS of 200 students and records the sample population that did their homework. So let's take a look using software. Um, that come up with these distributions. So um, the sampling distribution, remember that's of let's see here, how many did they do? It doesn't actually even, so there we go. We repeated this process 1,000 times. So they took 100 students from school one and then calculate the proportion in that sample and did that 1,000 times just to remind you what the sampling distribution means. So they did that, and they again the center is the parameter 0. 0.7. The spread, again, recall this formula, um, again, 70%, so it's 0.7 times 1 minus 0.7, so 0.3 over the number of students. So um, we got our spread. Our standard deviation was 0.0458. Same thing here. This is going to match the parameter, and we calculate that. We get 0.0354. And the center is just going to be, if I take um, 0.7 minus 0.5, I get my 0.2. But I have a question. How did they get that 0.058? Yeah, hopefully you recall from chapter, I want to say 6, um, that to figure out what that is, remember, we're going to have to take sigma of P1 squared plus sigma of P2 at squared, and that's going to equal sigma of P1 minus P2 squared. So it's kind of like, I don't know, Pythagorean theorem almost, if you want to think of that pattern, a squared plus b squared equals c squared. But it doesn't matter that we're subtracting or adding when we're talking about the standard deviations. When we add or subtract two distributions, we've got our spread ends up being that squared. So if I took 0.0458 squared plus 0.0354 squared and square rooted it, I'd get 0.058. That's how we get that. So, and then it looks like here, yeah, sorry, they just mentioned it right here, right? To find the mean, we just subtract the two means, and to find the sigma, the standard deviation, we got to square them and add them first. That's a kind of a common mistake, is not to do that. Um, just add them right off the bat or something like that. But no, we have to square them, add them, and then square root them. So recall some of the things that we needed to know. In order to be approximately normal, we had to have these that these n p1 n times 1 minus p1, etc. All those had to be at least 10. So in chapter 9 it was, just this and this, but now we've got two different um, statistics we're looking at, so it's got to be all of them. So that's why there's four of them. And then again, the mean, we just talked about that. We just subtract the two means. And now the standard deviation, where does this formula come from? Well, remember, um, sigma p1 was equal to um, square root of p1, 1 minus p1. If I could write a little bit better. Over n1. So notice if I take that and square it, I get that. If I do the same thing for p2 and square it, I get that one. And then we're just using this formula right here to end up with that formula at the end. So it's really just using the formulas that we've used before, all put together. And then we also need to check the 10% condition, right? If we're sampling, again, that's only if we're sampling without replacement that we have to do that, but because we're using some like approximately binomial computations in this as well. All right, so excuse me. So if I check all those things for the example that we were just working on, we notice that np1 equals 70, n1 times 1 minus p1 equals 30, etc. We're checking that all these numbers are bigger than or equal to 10. And they are, so we're good to go. It's approximately normal. And the mean, again, just subtract the two, and the standard deviation, I went through that calculation as well. All right, so when data come from two random samples or groups in a randomized experiment, the statistic p1 hat minus p2 hat is our best guess for the value of p1 minus p2. So again, these are, from our sample statistics versus our parameters over. I forget, you can't see my cursor. So there's our statistics versus our parameters, right? We can use our familiar formula where our statistic plus or minus critical value times standard deviation. Remember that was like, before it was p hat plus or minus z star, and then square root of p times 1 minus p over n. This is what we had before. Well, it's the exact same thing, except now instead of having p hat, we've got p1. It's p1 hat minus p2 hat, and that's going to be. I think we have the formula on the next page here, but yeah, all the way down here. So notice you have p1 minus p2 hat plus or minus z star times the standard deviation. Well, now the standard deviation is this guy, so this guy goes right here. And it's, like I said, it's very, very similar to what we've done in the past. And then again, we check if the normal condition is met, so we can use our normal distribution to try and figure this out. So. And so again, I guess I made a slight little error up here is because these are P1s, not P1 hats. But typically we won't know what P1 is and what P2 is because those are the actual population percentage that we're trying to figure out a lot of times, or that we're trying to use. So instead, we'll have to use our sample proportions. So notice they all have hats on them in our actual formula. So. And remember Z star, that same critical value, basically like it depends on what confidence interval we're going to do. Like, right, a 95% confidence interval was Z star was 1.96, because if we look it up in our table, that's what we find. So let's just do an example. So as part of the project, researchers conducted two surveys. First survey asked a random sample of 799 U.S. teens. So 799 teens about their use of social media and the internet. The second survey posed similar questions to a random sample of 2253 U.S. adults. Sorry, hopefully you couldn't hear the baby in the background, but so we have that many teens, that many adults. In these two studies, 80% of teens and 69% of adults used social networking sites. So that's kind of the important stuff that we're using here. All right, so calculate the standard error of the sampling distribution of the difference of sample proportion, so teens minus adults. What information does this value provide? So if we're looking at this, we're going to have to do our good old, um, square root. Well, here, they just have the work here. But again, that's the formula that we had up there, where we plug in 0.8 for P1 hat and 0.69 for P2 hat. And then we plug in these for the sample sizes, the 799 and the 2253. So we end up with 0.0172. So again, the difference in sample proportions of teens and adults who use social networking sites will typically be 0.0172 from the true differences. So again, that's just saying how far on average if we take that lots of different random samples of that many teens and adults. Typically, our value that we come up with for the difference in proportions would be with about 0.0172 from so about 1.7% away from the true value. All right, so and then B, construct and interpret a 95% confidence interval for the difference between the proportion of all U.S. teens and adults who use social networking sites. So again, P1 is going to represent the proportion of all teens who use social networking. P2, proportion of all adults. And we want to estimate the difference P1 minus P2 at a 95% confidence level. So remember, the whole thing that we're going to do is our statistic plus or minus our Z star essentially, and then our standard deviation. So we already have our standard deviation done. So we're going to have P1 minus P2. So it was, notice it's going to be 0.8 minus 0.69 plus or minus. Z star for a 95%, remember that's 1.96. We've used that quite a bit. You might have it memorized, maybe not. And times 0.0172. So that's the calculation we're going to do. So recall, in order to do all of this stuff, though, we need to check 10% rule. Are there more than 8,000 teens in the U.S.? They certainly are. Are there more than 22,000 adults? There certainly are. So the 10% rule is met. And then if we check, check our large counts, we need 0.8 times 799 to be greater than or equal to 10. Well, it is, right? And they have to do all the calculations down below, but so let me just go down and look at that. But basically, we got to check out all our requirements to make sure they're done. So let's see. Yeah, there are more than 8,000 teens. Yeah, there are more than 22,000 adults. We check our large counts, and we end up with these values here. They're all bigger than 10 by a long shot. And then they say note that the observed counts have to be whole numbers. Because again, you're not going to observe 159.8 teens that use social networking. All right, so we do a calculation. This is basically exactly what I said up above. And we end up with that as our interval, our confidence interval. So we are 95% confident that the true proportion of the difference lies between 0.076 and 0.144. And that's pretty much word for word what they say there. So again, that's basically saying that there's between a 7.6% and a 14.3% difference, or 14.4 depending on whether we use this number or this number. There's between that much, about that much difference between teens that use social networking and adults that use social networking. All right, one thing that's go to stat tests, and I'm going to go to 2 prop z int. So int for confidence interval, right? And we're doing two proportions, right? So we have two populations that we're looking at. So plug in 639, 799, 1555, and 2253. Put in our confidence level, which is 95%. Go ahead and calculate. And notice there we go. We have our answer, our interval right there at the top. So it's kind of nice, quick, and easy. But make sure you can tell what test we're doing here. So it's a two proportion z interval. That's kind of what the name of this thing is called. And then specify all the values that you used. Now, where did these numbers come from? So you might be wondering, wait a second, when we did this, there's maybe two prop z in 639, 799. Like, well, I can see where the 799 and 2253 come from. But where does x1 and x2 come from? Well, remember, think back to the original problem here. It said 799 US teens and 80% of them. So 0.8 times 799 gets me 639. And then if I do 0.69, because that's the number of percent of adults over there, times 2253, notice I get 1555. So 639 and 1555, notice if I go back in there, two zam z interval. Oh, sorry, two prop. That's what I meant to say, not sample. So stat tests to prop z int is what I meant to say. 639 and 1555. That's where those numbers come from. But this is real nice. You can use a calculator to do it real quickly. Just make sure, one of the things that we'll have to work on, it's kind of one of my things I've kind of lacked in class, making sure we worry about the names. This is a true proportion, two proportion z interval is what we're doing here. All right, so that was confidence intervals. Now we can look at significant tests. Just like, again, what we did in chapters 8 and 9. We did confidence intervals in 8, I think, and then significant tests in 9. Same deal, except we're doing both in both of them in one section here in chapter 10. So typically our null hypothesis in this will be that there is no difference between the populations, so that P1 minus P2 is equal to 0, which is the same as saying that they're equal. So that's going to be our null hypothesis that we're going to be dealing with in all of these cases. And then our alternative hypothesis will be that it's either not equal to 0, or it's smaller, or it's greater. So again, exactly the same as what we did last chapter. And the same rules apply when we're talking about proportions. It has to be random, 10% rule has to apply, and large counts rule has to apply. Now remember when we did this, remember this is still basically looking at z equals x minus mu over sigma. That's the very first z-score that we learned. This is the same idea, except, you know, x is always our statistic parameter. Remember, so our in this case, it's not going to be mu. It's going to be p, but or actually p1 or p1 minus p2, which in this case, in our null hypothesis, is equal to 0. So we have, again, our statistic, our parameter, and our standard deviation of our statistic. So that's why this right here is my x, p1 hat minus p2 hat. 0, again, I said the y up above. And we need our standard deviation of the statistic, which we talked about before. You know, square root of all that, you know, p minus times 1 minus p, etc. We're going to do a little bit of additional calculation here for the standard deviation, though, because sorry, I keep on getting interrupted. When we're looking at this, so the last thing I believe I was talking about, we had our statistic is there, our parameter is there, again, because we assume that P1 minus P2 is equal to 0. So again, we're assuming our null hypothesis is true. And then we need to figure out the standard deviation of the statistic. And that we got to use that based on our parameter. And so what we're going to do is we need to have a decent estimate of our parameter. Remember, back when we first did this, we kind of either used data from a previous study, or we just used a worst case scenario of 0.5. Well, here we can do a little bit better. We can look at it and we can figure out the pooled sample proportion. So basically just look at add up the number of successes in both samples and divide by the total number of individuals in both samples, and that'll give us a nice estimate for the parameter. So that's what we're going to do. That's going to go down here in what we use for the standard deviation of the statistic. So 2 sample z-test for difference between 2 proportions. So this, again, is a significance test. So that's why it's called the 2 sample z-test. Again, before it was a confidence interval, so it's a 2 sample z interval, right? But again, you can see the bottom here, that ends up being when we use this p hat sub c, that's our combined, our pooled resources. So let's go ahead and do an example, and hopefully it'll make sense. So researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not had breakfast. There are more than 1,500 students at each school. Again, they tell us that so our 10% rule is fulfilled, right? These data give convincing evidence at the alpha equals 0.05 level of a difference in the population proportions. All right, so our null hypothesis is that they're the same, and that's what it's always going to be. Our alternative hypothesis is that they're not the same. So first off, it was a simple random survey from each one, so it's random. 10% rule, well, 80 times 10 is 800, 150 times 10 is 1,500. There are more than 1,500 students in each school. So all those things apply. We can see that the 10% rule is met. And then large counts. Again, we ended up with 19 that, again, we're talking about had not eaten breakfast. So there were 19 had not eaten breakfast, and then that leaves us with 61 that had. And similarly, 26 did not, so that leaves us with 124 that had. So all those values are at least 10, so this condition is met. All right, so let's go ahead and do the calculation. So first off, we need to figure out what the P1 hat and P2 hat are. So 19 out of 80, right? There were 80 in our sample. 19 hadn't had breakfast. So we end up with, that's our proportion of students that did not have breakfast at School 1. And then 26 out of 150 had not at School 2, so that's our proportion there. So we end up, so P1 hat minus P2 hat ends up giving me, subtract those two, and I end up with 0.0642. Now again, the pooled population, this is what we're going to use where we, in the denominator, where we look at the standard deviation of the statistic. But if I look at, where does that come from again? We had 19 plus 26, so a total of 45 who had not eaten breakfast out of a total of 80 plus 150 students. So 45 out of 230, that's where that comes from, had not eaten breakfast. So we're going to use that as our proportion. Plug them all in, go ahead, and we end up with our z-score of 1.17. Now recall, what we're trying to do is figure out what percentage of samples would have more than, be further away than 1.17 standard deviations away from the mean. So we can look at the probability that z is greater than or equal to 1.17 and then just double it because of symmetry. So you could use your calculator. Let's just go ahead and use our calculator for this. So we go to second distribution, normal CDF, and lower, we want to know things that are bigger than 1.17. So 1.17, upper, something big, you could do 1E989 or 10,000 or something like that. Mu, this is, we've already converted everything to standard normal, so I could just do that. I get 0.121, that's the probability that's bigger than 1.17. We also need it, what if it's smaller than negative 1.17, so we're just going to double that. We end up with 0.242. And you'll notice you can get that from the table as well, or the calculator. So we end up 0.242. Remember our alpha in this was 0.05. So since our p-value is larger than that, we would fail to reject the null hypothesis. There's not convincing evidence that the people going without breakfast is different. So, all right, so how do we do this on the calculator? This is kind of nice. You can just do it real quick. Stat, tests, and I accidentally tried to do this earlier, I think. 2 prop z test, again, because we're testing this. So, it's clear. So if we look at this, we had 19 out of 80. We had 26 out of 150, I believe it was. And we want to know if they're not equal. That's our null hypothesis is that they're equal. So we're doing our test the other way. So we look at our z, our test statistic. Remember, z is our test statistic. So we get 1.17, and our p-value is 0.243. So that's a nice quick way of doing that. Just make sure you write everything that you need to about checking the tests and everything like that. You can use this stuff. All right, final thing for experiments, one of the biggest differences is that you don't need to check the 10% condition because you're basically, your population is the people in the experiment. And so you're exempted from having to use that, check that condition. And again, keep in mind, experiments can only be on, the results can only be generalized to people like those in the experiments. So, but we spent in a whole chapter on that. So last example, high levels of cholesterol in the blood are associated with higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? So they recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. So 2,051 men took the drug gemfibrozol to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. During the next 5 years, 56 men in the gemfibrozol group and 84 in the placebo group had heart attacks. Is this difference statistically significant at the alpha equals 0.01 level? So they're being pretty strict here, right? A smaller alpha, again, that's basically, think of, if you compare it to confidence intervals, that's like a 99% confidence interval. All right, so null hypothesis, there's no difference. The alternative hypothesis is we want to see that it reduces heart attacks, so we're going to look that it is less than 0. All right, so where where P1 is the proportion of people that took gemfibrozil, and P2 is the actual heart attack rate for those taking the placebo. All right, check our conditions again. Random, it was randomized. 10%, like I said, it's an experiment. There was no sampling involved. Large counts. So again, successes and failures or whatnot. Again, it's weird to say successes had a heart attack, but that's kind of what we're looking at. So it's 56, 84, 2030, sorry, not 2030, 2030 minus 84, which is bigger than 10, and 2051 minus 56, which is bigger than 10. So we're okay on that. So we look at our proportions, divide the two numbers, P1 hat, P2 hat, and then our pooled, our combined, so that C is for combined. Basically, again, 56 plus 84 over 2051 plus 2030. And that's where that comes from. So just basically, again, add the numerators here, add the denominators here. That's where those numbers came from. And we get that for 0.0343. That's, again, what we're going to use when we're calculating our standard deviation. But if we want to, we can just go ahead and go straight to, again, stat, tests, 2-prop z-test. Let's see here. Let me go up here. We had 56 out of 2051. And then we had 84 out of 2030. And this time we wanted to know we wanted P1 to be less than P2. Test statistic, negative 2.47. P is 0.0067. So notice this p-value is lower than 0.01. So there is convincing evidence that gemfibrozil did have basically we reject our null hypothesis, and we say there is convincing evidence that it had an effect. So, and that's basically it for this section.